Hello students, I am CG sir. Today in this lecture we will discuss about the double dual and the transpose of a linear transformation. Recall in the last lecture we have discussed about the dual space dual basis. So that means if V is a given vector space over some field F and it has a given basis, then V star is the collection of all linear functional from V to F. Then what will be the basis? That means corresponding to each basis of V we get another basis of V star, that is called the that is called the dual basis of that basis of V. So if I specify a basis in V, we will get a basis in V star. Now the question is reverse. That means is every basis of V star is the dual of some basis of V? You are given a basis this. That means is it the basis of some dual basis of some basis of this? We will prove it. So we state a theorem. Let F be a field and V be a finite dimensional vector space. Okay, be careful. Sometimes we require the V a finite dimensional vector space. Sometimes we do not require it is a finite dimensional vector space. Whenever we mention dimension of V is n or something like that, that means V should be finite dimensional. Otherwise, V is arbitrary vector space. That means finite or infinite dimensional. Here it is finite dimensional. Now, for each alpha belongs to V, we are defining a functional from V star to F, because V star is a vector space. How? The definition of L alpha is L alpha of F, because F are the elements of V star. The elements of V star are function from V to F. L alpha of F equal to F of alpha for all alpha belongs to V star. Then the conclusion is that means we have to understand what does it mean. V is a vector space, F is the field, then F, small f is a functional from V to F, alpha is carried to F of alpha by small f. Again, V star is another vector space, it is the collection of all such elements, all such functions. So F is a function, F is an element here. L alpha takes F to this element because it is again a vector space over F. In this way we define this mapping. Now the conclusion is that then the mapping T from V to V double star, now we are defining a mapping from T to V to V double star by T of alpha equal to L alpha, because alpha is an element here and L alpha is an L alpha, where does it lie? It is a functional from V star to F, so it lies in V star whole star. Okay, so T is a mapping from alpha to L alpha. We have to prove that T is an isomorphism between this and this. That means basically these two spaces are same. If in the sense of vector space, isomorphism means T will be a linear transformation which is 1 1 on 2, and two isomorphic space means they are same space. So first of all we have to prove that the T defined in this way is a linear transformation, sorry, L alpha is a linear transformation. Okay, then we have to prove that T is also a linear transformation. Then we have to prove that T is 1 1 on 2. Okay, now to check L alpha linear, let us take f and g, small f and g, two elements in V star. Okay, now and C be be a scalar. Now L alpha of Cf plus g, what will be this? By the definition of L alpha f, this is equal to f of alpha. So it will be this of alpha, Cf plus g of alpha. Again, f, g are elements of V star and V star is a vector space. So Cf plus g of alpha equal to Cf of alpha plus g of alpha. That is equal to C into f of alpha plus g of alpha. Again, f of alpha means L alpha of f according to the definition of L alpha. G of alpha means L alpha of g. Okay, so L alpha of Cf plus g equal to C into L alpha of f plus L alpha of g. That means L alpha is a linear functional on V star. Clear? Now the dimension of V is n, it is given, and for any non-zero vector alpha in V, look at this, since V dimension of V is n, so definitely dimension of V star will also be n. So you must get a non-zero element in the basis of V star. Non-zero element in V star means it will take some non-zero element alpha to some non-zero element. Otherwise, if f takes all elements of V to 0, then f must be zero functional. Okay, so since there exists non-zero functional in V star, from V star to f, in V star from V to f of alpha not equal to 0 for alpha not equal to 0. And if f of alpha not equal to 0, that means L of alpha of f, that will be not equal to 0. That means L alpha will again be a non-zero functional from V start to f, capital F. Now for L alpha non-zero, there exists f belongs to V star and alpha belong to V, such that f of alpha not equal to 0, because L alpha is non-zero functional means f alpha takes some small f to the non-zero element. Okay, some non-zero functional small f to the non-zero element. So definitely f of alpha not equal to 0, because if f of alpha equal to 0, L alpha of f will be the theta element, 0 element. So be careful in this portion. So that means from here we get L alpha equal to 0 if and only if alpha equal to 0, because L alpha is constructed depending on alpha. Okay, for each alpha we are, so each alpha gives birth of a linear functional. Clear? And if this alpha is non-zero quantity, L alpha will be a non-zero functional. That is if and only if condition. Now to check T linear, let us take alpha beta belongs to B and C belongs to F. We have to prove down T is linear. We are taking alpha beta in here and C be any scalar. Since V is a vector space, so C alpha plus beta is in V, and suppose this element is gamma. Now for each V f belongs to V star, look here, for each f belongs to V star, L gamma of f, that is by the definition of L alpha, this is f of gamma, that is equal to f of C alpha plus beta, that is C into f of alpha plus f of beta. Again f of alpha means L alpha of f of beta means L beta of f. So we can write it as C L alpha plus L of beta of f. That means L gamma of f equal to this of f means L gamma equal to C L alpha plus L beta. Okay. Thus T of, now the definition of T, look at this, T alpha equal to L alpha. We are using the definition of T. T of C alpha plus beta means T of gamma, this is gamma. Again T of gamma means L gamma. Again L gamma means C L alpha plus L beta. That's why we have calculated this portion. Actually this is used here. Okay, our target is to prove this. C into L alpha plus L beta, that is equal to L alpha means T of alpha, C into T of alpha plus T of beta. This implies T is a linear transformation from V into V double star. Next we will check T is 1 1 and on 2. Now T alpha equal to 0 if and only if alpha equal to 0. Clear? According to the definition of T alpha equal to L alpha. So T alpha equal to 0 if and only if L alpha equal to 0. Again, L alpha is 0 if and only if alpha equal to 0. That means T alpha is 0 if and only if alpha is 0, means T is a non-singular linear transformation. And this implies T is also 1 1. Again, dimension of V double star equal to dimension of V star equal to dimension of V equal to n. So all the dimensions are equal. So a 1 1 transformation from n dimensional space to n dimensional space is also onto. So T from V to V double star is 1 1 and onto linear transformation. Therefore, T is an isomorphism from V onto V double star. That is, V and V double star are isomorphic. From this theorem, we get two corollaries. Let F be a field and V be a finite dimensional vector space over the F. And L is a functional from V star to capital F. This is given. Then the conclusion is that there exists unique alpha. That means now for a given L, we will find a unique element alpha such that L is defined in this way, LF equal to F of alpha. Previously we have chosen alpha in V and we defined in this way. That means we get L. Here L is given, we are finding alpha. Next corollary, F be a field, V be a finite dimensional vector space. The conclusion is that each basis B star for V star. So the dual space, this is a basis, this is any basis. This basis is the dual of some basis B of V. So the statement from where we started today's lecture, that is, for each basis B star of V star is the dual of some basis B of V. This can be also proved by using the previous theorem. Next theorem, let F be a field, V be a finite dimensional vector space, and S be a subset of V. Okay, this implies S naught whole naught is the subspace of V spanned by S. S naught means the annihilator of S. Okay, that means the collection of functional from V to F which takes the elements of S to the 0 element, that is S naught. And we know that for any subset S of V, S naught is a subspace of V star. Okay, now S naught whole naught, it is a subspace, basically it is a subspace of V double star, and since we have proved V and V double star are same, so it is a subspace of V spanned by S, thus S which we started initially. Okay, so let W be a subspace of V spanned by S. We are taking W is any subspace which is spanned by the elements of S. That means S naught whole naught is naught. Our target is to prove W equal to S naught whole naught. Now, that means V S F, these elements goes to 0. Okay, this is our V star. So if it is our S naught, it is an element of, so if it is S naught. Okay, now suppose this is our S naught whole naught, means W, it is V means V double star, V equal to V star whole star. So according to the construction of this, the annihilator of this portion, it is these are the functional of V start to F. Okay, so W naught equal to S naught. That means this W is actually spanned by these elements. So the elements taken to 0 by small f, this small f will also take the elements of W to 0, because each element is a linear combination of the elements of this. Okay, so the space spanned by W and space spanned by S will be same. These are the spaces, both the spaces are here, this one, this thing. Again, from a previous now dimension of W plus dimension of W naught equal to dimension of V. That is n. Dimension of W naught plus dimension of W double naught equal to dimension of V star equal to n. So from here we get dimension of W equal to dimension of W naught. That means W equal to W naught, because W is a subspace of W naught whole naught. Clear? So you have to understand this portion. Now note that we have defined the hyperspace for a finite dimensional vector space. In the previous lecture, we have taken a vector space finite dimensional n, then any n minus 1 dimensional subspace of V is called a hyperspace or hyperplane. Now we will define a hyperspace for any arbitrary vector space. That means any finite or infinite dimensional. What is the definition? Let V be an arbitrary vector space. A maximal proper subspace of V is called a hyperspace. Maximal proper subspace. You heard the term maximal. That means V is a vector space. If W is a maximal proper subspace, then any other subspace Z containing W, either Z will be equal to W or Z equal to V. Okay, you heard this term from maximal ideal. That means there is no subspace between this subspace and V. There is no subspace. Okay, with respect to the subset operation, ordering operation. Theorem: let F be a field, V be an arbitrary vector space, finite or infinite dimensional. Small f from V to capital F be a functional, it is non-zero functional. And suppose NF, this is the null space of small f. Null space of small f means you know the kernel of small f, the elements of V which are taken to 0. This is a subspace of V. NF is a subspace of V. This NF, the conclusion is that this NF is a hyperspace of V. So for any functional, its kernel is a hyperspace of V. Conversely, every hyperspace of V is the null space of a non-unique, non-zero linear functional on V. Okay, so in this way you can find a hyperspace of any vector space. Now F, we have a lemma. This lemma is used to prove the next theorem, though we will not prove it. Let capital F be a field, V be a vector space, arbitrary vector space. Small f be a functional from V to F. G is another functional from V to F. Suppose G is equal to C into F for some C belongs to scalar. Okay, G can be written as this, and it is if and only if the null space of G contains the null space of F. Again, null space of G contains null space of F means F of alpha 0 implies G alpha equal to 0, because every element here is an element here. How to use this? We generalize this. Let capital F be a field, V be a vector space over the field F. G F1 F2 dot dot Fr, these are functionals from V to F. N N1 dot dot Nr, these are the null spaces of G F1 dot dot Fr respectively, and G is represented as C1 F1 plus dot dot Cr Fr, for these are the scalars C1 C2 Cr. Then the null space of G contains the intersection of null spaces of this, because null spaces are subspace and the intersection of subspaces is a subspace, again a subspace. So this subspace contains this. Okay, fine. Now we'll finish it by defining the transpose and proving a theorem. Transpose, we have heard the transpose of a matrix. Here we define the transpose of a linear transformation. Let F be a field, V and W are two vector spaces, arbitrary vector spaces over the field F. For each T, for each linear transformation, there exists a unique transformation T transpose W star to V star such that TTG of alpha equal to G of T of alpha for all G belongs to W star and alpha belongs to V. Be careful. T is a linear transformation from V to W. So T takes alpha to T alpha. Clear? Now for this, the conclusion is that this is W star, means the collection of all linear function from W to F. This is V star, collection of all linear transformation from V to F. So G is an element in W star. TT, it is a mapping. This maps G to TTG. Now the action, now TTG is an element of V star, that means it is again a functional from V to F. So V, this is F, TTG will act here and gives an element here, and G is a functional in W star, means G maps from W to F. G, T alpha is an element. T alpha is taken to G of T alpha by small g. That element will be TTG of alpha. In this way we are defining this. Be careful. So first of all we have to check that TT is a linear transformation. So to prove TT is a linear transformation, we will take two arbitrary elements G and H from here and C is scalar. Now TT of CG plus H of alpha, that is according to the definition of TT, this is the definition of TTG of alpha equal to G of T alpha. So we'll write CG plus H of T alpha. Clear? Again CG plus H of T alpha means these are the functional in W. So CG of T alpha plus H of T alpha. Again we are using the definition of TT, that is C TT of G of alpha plus TTH of alpha. So it is represented as C TTG plus TTH of alpha. That means TT this of alpha equal to this of alpha, means TT of CG plus H equal to this. So TT is a linear transformation. Clear? Now we have an observation. T from V to W, it is a linear transformation. G from W to F, it is linear functional. So its composition mapping from V to F, that is GT, G of T from V to F, this is also linear transformation. Thus T induces TTG. That means for any T we are getting TTG from W star to V star, which is defined in this way: TTG of alpha equal to G of T alpha for all alpha belongs to V. So since for each T we are getting TT, which is defined by this TT is called the transpose of the linear transformation T. It is also called the adjoint of the linear transformation, but usually we will use this term transpose. Clear? And this is defined for any arbitrary vector space. Now we have a theorem: F be a field, V and W are two vector spaces, arbitrary. T is a linear transformation from V to W. Then the conclusion is that the null space of TT is the annihilator of the range of T. Okay, the null space of the null space of tt means the elements here which are taken to the theta here, that is the null space of tt, and that is a subspace of w star, and this subspace of w star is the annihilator of range of t. That subspace will be the annihilator of the range of t. So its range will be a subspace of w. Okay, its annihilator means any subset which is the collection which are taken to 0 to f. Okay, further, v and w are two finite dimensional vector space. Here we are taking finite dimensional. Then rank of this transformation and rank of t will be equal, and range of t transpose is the annihilator of the null space of t. As we have null space of t transpose is the annihilator of the range of t, here range of t transpose is the annihilator of the null space of t. Next theorem, let F be a field, V and W are two vector spaces, both are finite dimensional, dimension of V is n, dimension of W is m. B and B star, B is the basis of V, B star is the dual basis of V star. Similarly, B dash is the dimension basis of W, ordered basis, and B dash star is the dual basis of W star. T is a linear transformation from V to W, and the matrix of T with respect to this and this basis is, suppose capital A, the matrix of T transpose from B dash star, we have to write first this, then this, B dash star, B star will be B. Now how they are related, A and B matrix, that is Bij equal to Aj. This is actually the transpose concept, as you know from the previous class. So from this definition actually transpose of matrix is defined. Okay, in this way the matrix obtained is called the transpose actually. Now we will define the transpose of a matrix. The transpose of an m cross n matrix capital A over the field A is the n cross m matrix, the order is reversed, A transpose, it is written by A transpose, such that ATIJ equal to AJI, where these are the elements of the matrix capital A. Clear? Now the last theorem of this chapter, F be any field and A be an m cross n matrix with the entries from capital F, any field, then the row rank of capital A equal to column rank of capital A. That means the vector space spanned by the row vectors, by the rows of capital A, and the vector space spanned by the column of capital A have the same dimension. This concludes here. Okay, and this ends this chapter. Thank you.